Okay, good afternoon. I'm Rupesh Gupta, Senior Engineer at LinkedIn, and I'm going to talk about email volume optimization, which is a joint work with five of my brilliant colleagues, Gonfeng, Xiaoping, Ravi, Xiaoyu, and Romer. So as you must know, LinkedIn operates the largest online professional networking service. We provide members with an easy way to connect with each other and exchange information. Information is typically exchanged by sending private messages, uploading and sharing rich media, self-organizing into interest groups where people typically ask and answer questions, and also subscribing to channels which deliver news on some topic of interest. So since there is a huge flow of information, we provide several services for our members to keep up with this information. These services are categorized typically into two kinds. The first one is pull model based in-app services like the feed or in-app notifications. The user is required to be actively logged into the mobile or web application to access this information. And the other one is push model based content distribution services like email and push notifications, where the user is not required to be actively logged into the mobile or web application. So conventionally, members can subscribe to receive email communication regarding news, connection requests, memberships, event notifications, and several other things like jobs you may be interested in or people you may know. So what ends up happening is that this results in a very large number of various types of messages that need to be delivered to a member. So our vision is to go from a world of uncontrolled distribution of various types of messages to a world where we deliver the right volume of the right kind of email at the right time, through the right channel, and at the right frequency. And each of these problems, like volume optimization, delivery time optimization, channel selection, and frequency control, pose unique challenges. Today, I'm only going to talk about volume optimization in detail. So in simple words, the problem of volume optimization can be described as follows. So given a pool of generated messages or emails where each email is targeted to a particular user, we want to identify the emails which can be dropped and the emails which must be sent out. So to be able to achieve this objective, we first need to understand the role of emails in the ecosystem of a networking service. So let's start with the cost-benefit analysis of sending emails. So we conducted an experiment where each generated email was dropped at random. So when an email gets generated, we just toss a coin and drop it if the coin says heads and send it across if the coin says tails. So as you can see here, we observed a very huge loss in page views across all of our product verticals in this bucket, which we call the random drop bucket. So here the comparison is being made against the bucket where an email is randomly dropped versus the bucket where every generated email is sent out. So there is a pretty significant loss. And so it's quite clear that there is a lot of upside to sending emails. But what's the downside? So when a user receives an email, she can positively interact with the email by viewing the email or clicking a link within the email. And clicking a link within the email typically brings her to the mobile or web application. But the user can also react negatively to an email by, say, ignoring the email, or clicking on the unsubscribe option within the email, or reporting the email as spam to the email service provider. So for example, when you receive an email on Gmail, you could report the email as spam to the service provider, to the Gmail in this case. And we observed a 45% more, sorry. We observed 45% more number of negative responses to emails in the send all bucket versus the random drop bucket. And if you think about it, it's not really something unexpected, because if you send more email, you do expect to see more responses, both positive and negative. But the difference is that unlike a positive response, the scope of a negative response does not end at a particular email. So for example, if a member unsubscribes, or rather clicks on the unsubscribe option, we lose the ability to send emails to that member in the future. And worse, if a lot of members report emails as spam from a particular sender to their email service provider, then the service provider might just block all emails from that sender. So for example, if let's say a lot of people who use Gmail start marking emails from LinkedIn as spam, then Gmail might just block all emails from LinkedIn altogether. And these kind of deliverability issues are in general very difficult to resolve. So to summarize, emails drive engagement. So it's not like you cannot just stop all emails. You cannot just say, I'm just not going to send any more email from tomorrow, because it will affect the growth of the networking service. But excessive email can have severe negative consequences, like people unsubscribing or people reporting emails as spam. So it should be quite clear that we would need some smart algorithms to identify what emails must be sent out and what emails can be dropped. So once again, the problem of volume optimization can be described in simple words as follows. Given a pool of generated emails, where each email is targeted to a particular user, we want to identify the emails which can be dropped. So ideally, we would like to minimize the number of emails sent, and at the same time, maximize the positive outcome of sending an email and minimize the negative outcome. So these kinds of problems where we are trying to optimize over several metrics are called multi-objective optimization problems, and they're typically formulated in this way. So we will specify one of the metrics as the objective, and the rest of the metrics go into constraints. So in this particular case, we have chosen downstream session, that is a session which begins with a click on an email as our positive outcome of sending emails, and a complaint, that is an unsubscribe or reporting of an email as spam, as the negative outcome. So we have specified a lower bound on downstream sessions because we want to maximize this metric, and we have specified an upper bound on complaints because we want to minimize this metric. And note that we are writing down this problem for the pool of emails that was generated over a specific time frame. So in our case, we choose a time frame of 1 week. So this problem will be written down for the set of emails which will be generated over a 1 week period. To express this problem mathematically, let's say for each email E, ZE is the probability of sending the email, SE is the probability of a downstream session, that is probability that a session starts from a click on an email, given E is sent, and CE is the probability of complaint from E, given E is sent. Then it's pretty straightforward to see that the expected number of sends is going to be summation over all these emails of the probability of sending each email E. The expected number of sessions is going to be probability of sending each email E times the probability of a session from email E. And expected number of complaints is going to be the probability of sending each email E times the probability of complaint from email E. So this was the problem that we wanted to solve, and here is how we have been able to express it mathematically. So minimize sends, which has been represented as minimize summation over EZE, such that downstream sessions are no less than a target, and it can be specified as summation over ZESE being greater than some target, and complaints being no more than a tolerance level, which has been expressed as summation over ZECE being less than a tolerance level. And we have added one additional constraint here, which is to enforce that ZE is a probability. So it's ZE, each of these ZEs should be between 0 and 1. So as you can see, this is a very straightforward and simple looking linear program which could be solved for ZE, that is the probability with which each email should be sent out. But there is a problem here. The problem is that we do not have access to this pool of emails E that will be generated in the upcoming week. So remember that when we wrote down the linear program, we assumed that we have access to this entire pool of generated emails. But actually we do not have access to this pool because the emails are not yet generated. So here is how we solve this problem. We observe that the distribution of our emails, generated emails, does not change much week over week. So we just use the pool of emails that was generated in the previous week as a forecast for the email that will be generated in the next week. But again, this does not really solve the entire problem because we still don't know what ZE should be for every email that actually gets generated. So to overcome this problem, we use a primal to dual trick, which has been introduced in this paper. It's a very fancy trick and works really well in practice. So the way it works is we first add an extra quadratic term to the objective. And you can think of this as a regularization term. So this was the original objective, and we have added a quadratic term here, which is like a regularization term, where Q is a prior on the send probability, and gamma is the regularization parameter. And this, adding this regularization term will help us obtain a relation between the primal and the dual solutions in this way. So if we write down the Lagrangian, it can be written in this way, where this is the objective and the constraints have been added here. We have left out the probability constraint outside of this Lagrangian because it helps us make the computation somewhat easier. So at the point of optimality, we know that we can take the derivative of this Lagrangian and set it to 0. And if we do that, we obtain this relation between the primal and the dual solutions. So now, in this solution, if we set gamma, which is the regularization term, to be very close to 0 so that it does not play a very important role, then we obtain a very simple and intuitive rule which for every email E. So this decision rule just says that if the probability of a session minus mu star over nu star times probability of a complaint is greater than 1 over mu star, then we send email E, else we drop email E. So mu star and nu star are the dual solutions, and SE and CE are the probability of session from email E and the probability of complaint from email E respectively. So intuitively, what we are saying here is that email E is sent only if the expected positive outcome, that is a session, exceeds the weighted expected negative outcome, that is a complaint, by a threshold, which is quite intuitive in this case. So you want the positive outcome to exceed the weighted negative outcome by some threshold. Then you send the email, otherwise you drop the email. So to summarize, what we have done here, we've solved the multi-objective optimization using the set of emails that was generated in the past week, and obtain the dual solutions mu star and nu star. And then for every email E that gets generated in the upcoming week, we will make a decision in this way. So as you can see, this is a very simple decision-making process once mu star and nu star are known to us. And what I've not yet explained is how we obtain these probability of session and probability of complaint for each email E. And this is a relatively simple prediction problem. To obtain these predictions, probability of session and probability of complaint for email E, we trained 2 logistic regression models with 4 broad categories of features. The first one is the targeted users profile features, such as members, locale, age. Just to remind you, whenever an email gets generated, it's always generated for a specific targeted user. So we always include not just the email features, but also the features of the targeted user when we are coming up with these prediction models. So we have targeted users profile features, targeted users in-app activity features, such as the members' last visit time, the number of sessions over the past week, past month, the targeted users' past experience with emails, such as number of emails received in the past week, number of emails clicked in the past week, and email message features such as the type of message, the language of message, length of message. So as we saw that the decision algorithm is very simple, and this actually leads to a very, very simple system design as well. So the system design looks like this. So depending on a member subscription settings, the message generator will produce a message for the member. So for example, if a member subscribes to network updates, then typically a message is generated once a week, which contains important updates pertaining to the member's connections, such as job changes, work anniversaries, profile updates. And then this message is passed down to the response prediction engine along with the ID of the target user. So the response prediction engine will extract the message features from this message to create a partial feature vector and then append the member features from this tracking data store. So this feature vector is then used in the response prediction models to predict the expected responses, the probability of session and the probability of complaint. And these predictions are then passed down to the volume optimization decision engine, which will make the final send drop decision based on the mu coefficients using the simple decision rule that we saw earlier. And so the members' interactions with the received emails, along with the profile of the member and the activity data of the member, are all recorded in this tracking data store. Snapshots of this database are then loaded into Hadoop. The snapshot data is used in the response prediction model trainer for training these response prediction models in Spark. And then these models are fed into the response prediction engine, as well as the mu solver here. The mu solver will then employ these models on the training dataset for predicting, for basically getting the optimal mu coefficients, the mu star and nu star, which are passed to the VO decision engine. So using this approach, we have been able to achieve very significant reduction in email volume. We have been able to get about a 40% reduction in email volume at the expense of just 2% loss in downstream sessions. And at the same time, we have reduced complaints. We have reduced complaints by about 40%. So the blue lines here are the constraints that we set in the multi-objective optimization formulation, and the red line is the A/B test result. So for example, here we said that we want to minimize sends such that we do not lose any more than 1.5% of downstream sessions, and we would not tolerate more than 60% of the complaints if all the emails were sent out. So as you can see, there's a significant reduction in email volume and complaints while losing very little of the downstream sessions. So here are the takeaways from this talk. Emails deliver significant value to members and drive engagement, but excessive email results in increased unsubscribes and spam report actions. And volume optimization can be formulated as a multi-objective optimization problem with the objective of minimizing emails while satisfying constraints on the positive and negative consequences of email. In our case, we chose a downstream session as the positive consequence and complaint as a negative consequence. And with certain approximations and tricks that we used here, the volume optimization system is extremely simple, and so is the decision rule. And this approach is, we have seen that it's quite effective in online A/B tests. That's it. Thank you.
Hi, interesting paper. I have a question about SE and CE. You said you used logistic regression to compute those values.
Right.
Can you talk more about that? I mean, why did you have to use logistic regression? You could just have a simple rule saying, upon clicking an email, if a user interacted with certain number of, activity modules or liked something, that constitutes as a successful session.
No, but we have to make a prediction, right? In this case, it's not retrospective because
Okay.
because we are trying to solve this problem for the set of emails that will be generated and potentially sent out. So we would have to have some prediction models which can predict the probability of session and the probability of complaint for every email.
Okay, thank you.
Two quick questions. One is, did you find a difference between the short run and long run effects of changing the volume of email? And secondly, was there much difference between the offline and online predictions of the model?
So the first question is, did the model performance degrade over time? Is that what you're trying to ask?
No, I mean, when you decrease the volume of email in the experiment, on the first day and the seventh day or after a month or something, were there changes in response to that intervention?
The user responses.
Exactly.
Yeah, the user responses do change when we reduce email volume, because in general, if you send too much email, the CTR per email goes down. So if you reduce email, the CTR per email tends to go up, which is why it's important to retrain the models using the latest activity features of each user. And your second question was?
Whether when you put the model online, whether the offline predictions were very close to what you actually found.
Yes, we have seen that we do get results which are very close to the constraints that we set in the optimization.
Right.
Yeah, it tends to work pretty well. Although there are approximations involved, we did not solve this problem for the set of emails that did get generated for the upcoming week. But since the distribution does not change much and the trick that we use here works pretty well, we don't see a pretty big delta between the constraints and the A/B test results.
Any other questions? Let's thanks.